October 29th. The day has arrived. For the first time since its discovery, 3I Atlas, the third confirmed interstellar object to ever enter our solar system, has vanished completely from human observation. As of this hour, it's behind the Sun, positioned in what astronomers call solar conjunction, the moment when our star itself blocks every direct line of sight. No telescope, no probe, no radar can see it. The universe has gone silent around it. For weeks, scientists have anticipated this exact window, not with comfort, but with unease, because during conjunction, we lose not only visibility but control. The Sun's plasma storms saturate radio frequencies. Optical sensors are blinded by glare. Even the most advanced instruments aboard the James Webb Space Telescope and the Parker Solar Probe can't safely collect new data. The object that's been accelerating toward the inner system, showing energy signatures no one can fully explain, is now hidden, just as it enters the region of maximum heat and gravitational stress. In theory, this is just an observational pause. In practice, it's a blackout at the worst possible moment. The object's composition remains uncertain. Its behaviour before disappearing, including a persistent sun-facing jet and fluctuating infrared output, defied the models used to describe natural comets. If anything unusual happens behind the Sun, we won't know until it re-emerges. Astronomers call this interval the blind curve. What happens here could decide whether 3I Atlas is remembered as a natural relic from another star, or as something that changed our understanding of what drifts between them. And now, as the light of the Sun consumes its path, we're forced to ask a simple question. What exactly is happening out there, right now, beyond the glare? Every telescope on Earth is now blind. The moment 3I Atlas slipped behind the solar disk, the entire arsenal of modern astronomy, optical, infrared, radio, lost direct contact with the object. For the first time since it was discovered, the sky offers no data, no visual confirmation, not even a spectral echo. It's as if the object never existed, but this blindness isn't a coincidence. It's a geometric inevitability, one that happens whenever a celestial body aligns too closely with the Sun from Earth's perspective. In astronomical terms, it's called solar conjunction, a period when the Sun's radiation and gravitational dominance overwhelm every signal trying to pass through. During this window, the Sun's light doesn't just outshine other objects, it corrupts the very instruments designed to see them. Sensors that normally detect faint traces of reflected light or heat are saturated by solar glare. Even the tiniest attempt to point a telescope near that direction risks burning its optics. The last usable images of 3I Atlas came in yesterday, October 28th, captured by both ground-based observatories and deep space satellites before the Sun's interference grew too strong. Since then, nothing. For the next several days, possibly up to a week, the interstellar object will remain hidden in that blinding zone, invisible to any direct observation. The situation is, in some sense, routine. Mars, Mercury, even Earth communication probes have gone through similar blind spots during conjunction. But the timing makes this particular blackout deeply unsettling, because 3I Atlas entered conjunction right as it reached the closest point to the Sun in its trajectory, the region of maximum energy, maximum heat, and maximum potential transformation. To understand why that's so important, imagine the inner solar system as a furnace. Any object approaching it, especially one not native to our system, faces extreme physical stress. Radiation pressure intensifies, tidal forces rise sharply, temperatures soar beyond anything experienced in the outer system. For a normal comet, this stage would mean sublimation, the release of gases and dust as the ice within vaporizes. But 3I Atlas has never behaved like a normal comet. Its spectral emissions, especially in the nickel and carbon bands, suggested a composition that reacts differently to heat. Instead of dissipating uniformly, it produced stable, directional jets, one of which pointed almost exactly toward the Sun. That anomaly alone has kept scientists arguing for months about whether the object's activity is natural or artificially modulated. Now, during conjunction, there's no way to verify what that jet is doing. If it intensifies, fades, or changes direction, we won't know until visibility resumes. The data blackout effectively seals a critical segment of its journey from human record. The object is travelling through a region where solar wind pressure, radiation flux, and gravitational curvature all peak. In simpler terms, It's undergoing its most dramatic transformation yet, and we can't see any of it. At the Deep Space Network control centers, operators are monitoring background noise rather than images. The solar corona produces a torrent of electromagnetic interference, making any attempt at narrowband communication almost useless. Signals bounce, scatter, and dissolve. It's not just the optical systems that are blind, the entire communication infrastructure is. Even if 3i Atlas emitted a radio signal of its own, it would be buried beneath the sun's roaring static. This silence has become a stage for speculation. Some astronomers remain calm, reminding the public that conjunction is simply a pause in observation. Others, however, see it as an opportunity, an unsupervised interval during which the object might reveal properties hidden from our view. There's an unspoken tension, the sense that something decisive might be happening behind the curtain of light. Consider how rare this alignment is. The object's trajectory intersects the Sun-Earth line at almost 0 degrees, an extraordinarily precise configuration. Most interstellar visitors, like Oumuamua or Borisov, pass through at higher inclinations, never fully vanishing behind the Sun. 3i Atlas, however, took a nearly Koplaner route, slipping exactly into the region that maximizes both solar influence and observational obscurity. To some orbital dynamicists, that's an accident of celestial mechanics. To others, it looks uncomfortably deliberate. During conjunctions of this kind, observatories rely on indirect methods. One of them is solar occultation spectroscopy, measuring how sunlight, filtered through an object's faint coma or tail, changes in spectral composition. Unfortunately, even that tool is unavailable right now. The sun's brightness drowns out any detectable modulation. Only after the object emerges can scientists compare pre- and post-conjunction spectra to infer what happened while it was hidden. At the European Space Operations Centre, teams monitoring the Solar and Heliospheric Observatory, SOHO, and the Solar Orbiter have narrowed their instruments' fields, hoping to catch the faintest scatter at the sun's edge. But the probability of success is nearly 0. The instruments are designed to observe coronal activity, not a dim, fast-moving object buried in glare. For all practical purposes, 3i Atlas has entered what scientists call an information eclipse. This eclipse raises a problem of timing. The next available observation window opens in roughly 6 days, once the object moves far enough beyond the sun's limb. By then, its behavior could have changed dramatically. Its brightness could drop, suggesting fragmentation or surge, indicating increased outgassing or reflective surface exposure. Either scenario would rewrite the current models. But at this moment, we're operating entirely in the dark. It's not the first time space agencies have faced a blackout at a critical juncture. During the Mars solar conjunctions of 2015 and 2021, NASA suspended all direct commands to rovers and orbiters for safety reasons. Even automated systems were left on standby until the interference subsided. But those missions involved predictable, well-understood objects. 3i Atlas is neither predictable nor understood. It's a new category altogether, an interstellar body with unknown internal composition, untested resilience, and unexplained energy patterns. In the last transmitted images, astronomers noticed faint shifts in its coma's geometry. The jets appeared more concentrated, almost filamentary, extending at precise angles relative to solar incidence. That detail sparked theories that the object might be rotating faster than they initially calculated, or that the jets themselves were generating torque. If that's true, conjunction might amplify these dynamics as solar radiation peaks. The sun could trigger rotational instability, or, if the jets are somehow regulated, a controlled reorientation. Either possibility remains hidden until the object reappears. For now, observatories are turning to simulation. At the Harvard-Smithsonian Center for Astrophysics, models are running on supercomputers to predict potential thermal responses. One simulation assumes a porous, volatile-rich composition, essentially a frozen conglomerate. In that scenario, the heat flux at perihelion would cause significant mass loss, perhaps leading to disintegration. Another simulation treats 3i Atlas as a dense, metallic core with a refractory crust. That version remains intact, shedding only thin layers while maintaining structural stability. The outcomes diverge completely. Without fresh data, no one can confirm which model is correct. The blackout also interrupts a major line of investigation: spectroscopy of unusual nickel and carbon compounds. Earlier readings hinted at the presence of nickel tetracarbonyl, a complex compound rarely found in natural contexts due to its volatility under heat. Detecting it again during perihelion would have been crucial to confirm the chemical anomaly. But spectroscopy depends on line-of-sight observation, and the Sun has severed that line. By the time the object emerges, temperatures may have already broken down such compounds, erasing their signatures. Meanwhile, agencies have gone quiet. NASA, ESA and the IAU have released no public updates since October 26th. Internal reports likely exist, but nothing official has surfaced. This silence fuels public speculation across forums and independent observatories. Some amateurs claim to detect faint perturbations in the solar corona corresponding to 3I Atlas's position, but professionals dismiss them as instrumental artifacts. Still, the timing of the agency's pause feels deliberate. It mirrors the object's own disappearance, a synchronized withdrawal from visibility. In communication networks, analysts are watching solar noise patterns for anomalies. Theoretically, if 3I Atlas interacts with the solar wind in a unique way, say by reflecting or absorbing charged particles differently, it could leave a trace in coronal mass ejection, CME readings. So far, no such trace has been confirmed, but the idea underscores how desperate scientists have become to detect something during this silent passage. At the Jet Propulsion Laboratory, the team responsible for monitoring interstellar trajectories is recalibrating future observation schedules. The moment visibility resumes, telescopes from Chile to Hawaii will pivot instantly toward the re-emerging zone. Timing is everything. A few hours' delay could mean missing the first glimpse, an event that might reveal whether the object's brightness or path has changed. Small deviations in trajectory can indicate powerful forces at work, either natural outgassing asymmetry or active control mechanisms. The term solar blind spot might sound temporary, but in the context of 3I Atlas, it carries existential weight. This object, possibly tens of billions of tons in mass, moving at interstellar velocity, is currently unmonitored as it grazes our star's domain. It's a situation that makes even seasoned astrophysicists uneasy, because while celestial mechanics can predict where it should be, no one can guarantee what it will become. Consider also the psychological dimension. For months, the scientific community and the public have watched this object approach, collecting data, theorizing, debating. That steady stream of information built a sense of familiarity, a pattern, a rhythm of updates. Now suddenly that rhythm has stopped. The silence feels unnatural, almost engineered. Humanity's most advanced eyes are staring into the brightest light in the solar system, and behind that glare, an alien object moves unseen. This is the paradox of observation. The closer an object comes to the Sun, the more we need to see it, the less we can. Every degree of proximity blinds us further. The Sun becomes both a source of illumination and the ultimate shroud, and as of today, 3I Atlas has crossed that line. When it emerges again, we'll face a new set of questions. Will it appear intact or fragmented? Will its brightness match the predicted curve, or will it defy expectations once again? Most importantly, will its trajectory remain consistent with the purely gravitational model, or will we find that something altered its path while hidden from view? Until then, every telescope waits, every sensor idles, every analyst watches the solar limb for a flicker of change. The blind spot has begun. What happens next depends entirely on what 3I Atlas is doing in the invisible furnace beyond the Sun's edge. The Sun has always been a crucible, a place where matter reveals its true nature under impossible heat. Every object that dares approach it faces the same test, whether it can endure the light. Today, 3I Atlas is taking that test at full force. As it moves through the inner corona, temperatures in its immediate environment soar past 2000 degrees Celsius. Solar radiation, plasma flows, and charged particles slam into its surface at supersonic velocities. If it's made of ice and dust like an ordinary comet, it should be disintegrating by now. But the truth is, we don't know what's happening. We can't see it. All we can do is calculate what physics says should occur, and compare it to what 3I Atlas has already defied. When an interstellar body enters the inner heliosphere, it encounters three overlapping forces: thermal stress, gravitational compression, and radiation pressure. Together, they form a gauntlet capable of breaking apart even iron-rich asteroids. Most natural objects flare briefly, lose their volatile components, and leave behind a trail of vapor. 3i Atlas, however, has a record of surviving conditions that should have stripped it bare. Its previous solar passes already revealed a strange resilience, a surface that not only endured but seemed to emit structured, controlled jets of material. Those jets weren't random, they were periodic, directional, and in some cases precisely aligned with solar vectors. That pattern suggests either an extremely stable internal structure or something actively regulating its reactions. Now that the object is deep within the Sun's heat zone, astronomers are recalculating what those earlier emissions might mean. The key variable is albedo, the measure of reflectivity. A higher albedo means more light is reflected, less is absorbed. If 3i Atlas possesses a surface with metallic or crystalline reflectivity, it could withstand far greater radiation levels than a typical comet nucleus. That might explain why its spectral reading showed nickel and carbon compounds uncommon in volatile-rich bodies. These elements, especially nickel-based alloys, have high melting points and unusual magnetic properties. Here's where things become truly strange. Nickel tetracarbonyl, one of the compounds tentatively identified in the object's emissions, decomposes at around 180 degrees Celsius under solar exposure. At the current distance from the Sun, that compound shouldn't survive a millisecond. Yet earlier readings showed its spectral lines persisting, even as 3i Atlas approached the inner orbits. Either those detections were misinterpreted, or the object continuously regenerates the compound through chemical or electrochemical processes. Both explanations raise questions that border on the extraordinary. Imagine an object composed not of fragile ice but of layered metallic composites. As it faces the Sun, the outer strata would oxidize and flake away, revealing new layers beneath, each acting as a thermal buffer. That kind of structure isn't impossible in nature, but it's rare. Iron meteorites show partial analogues. Nickel-iron alloys with Widman-Stetton patterns formed under immense slow-cooling conditions in other star systems. However, 3i Atlas's emissions don't fit those profiles neatly. The light curves recorded before conjunction showed oscillations that suggested active thermal regulation, bursts of heat followed by cooling intervals, as if the object were venting energy in pulses rather than in continuous sublimation. To visualize this, picture a dark body approaching the Sun. Its surface glows faintly blue, then dims, then flares again, in a rhythm that's too regular to be random. Each flare corresponds to a spike in infrared readings, like controlled exhalations. Some astrophysicists propose that these pulses could be rotational, a tumbling motion exposing alternating materials to sunlight. Others think the timing is too precise. If the venting cycles follow a thermal equilibrium pattern, it implies an internal mechanism capable of responding dynamically to heat input. That would be extraordinary, not for a spacecraft, but for a natural object drifting between stars. Meanwhile, computer models attempt to simulate what's happening right now, behind the Sun. One model predicts catastrophic thermal fracturing. As the surface heats unevenly, internal stresses could cause cracking, releasing pressurized gases trapped within. Another predicts a smooth transition, with the outer crust vaporizing gradually, creating a thin, reflective shell of metallic vapor. If that's correct, the object might emerge brighter, not dimmer, when it reappears. That would be a paradox. A body growing more luminous after enduring its closest approach to the Sun. Heat also changes motion. Outgassing jets can alter trajectory, subtly but measurably. For 3i Atlas, a shift of even a few meters per second could accumulate into a major orbital deviation over astronomical distances. Tracking that deviation once visibility returns will be essential. If its path has changed more than gravitational models predict, something active occurred during the blind period. The problem is that we'll only know days from now, long after the fact. In the absence of real-time observation, scientists are combing through historical analogues. The case of comet YSON in 2013 offers a grim comparison. YSON was expected to survive its perihelion pass, but disintegrated completely within hours, leaving only a trail of dust. 3i Atlas, by contrast, has already survived one intense perihelion and is orders of magnitude denser. If it behaves differently, it could redefine how we classify interstellar bodies. But there's an even deeper mystery tied to its temperature curve. When astronomers last measured its infrared output, the readings didn't follow a normal heating gradient. As it neared the Sun, its surface temperature appeared to plateau, stabilizing instead of spiking. That's thermodynamically impossible for an inert object. In natural terms, it should have heated continuously until sublimation began. The plateau suggests either an insulating phenomenon, perhaps an electromagnetic sheath or magnetic field interaction, or some form of energy redistribution. In other words, the object might be managing the heat. The Sun's environment amplifies every detail. Radiation pressure near perihelion exerts measurable force, enough to deflect small spacecraft solar sails. If 3I Atlas's surface is reflective and structured, it might interact with that radiation more efficiently than a typical asteroid. It could even experience controlled momentum adjustments. To some researchers, that's the key. They propose that 3I Atlas might possess geometric symmetry, optimized for stability in solar flux, perhaps elongated or flattened to balance radiation torque. Such precision would be a staggering coincidence for a random fragment of rock. At this stage, astrophysicists divide into two camps. One argues that every anomaly has a natural explanation we just haven't modelled correctly. The other insists that the cumulative pattern, nickel emissions, directed jets, stable heat management, cannot be coincidence. The conjunction amplifies this divide because there's no new data to settle it. Both sides can project their theories freely into the silence, and so the debate shifts from observation to belief. If the object is natural, its survival or destruction during this heat encounter will depend purely on composition. But if it's not, if it's something constructed, something designed to endure stellar proximity, then this moment behind the Sun isn't just survival, it's purpose. Because hiding there, shielded by solar radiation, it's effectively invisible to all instruments. That's the perfect condition for maneuver, adjustment or emission shield testing. A few mission planners have even discussed the hypothetical. If you wanted to send a probe into a star system undetected, you would use solar conjunction as cover. The Sun's glare makes tracking impossible, and its electromagnetic chaos masks any signal. Whether by coincidence or by intent, 3I Atlas is now in that exact configuration. Thermal modelling also touches on the object's internal density. If it's hollow, heat conduction would differ drastically compared to a solid mass. Hollow structures cool more efficiently, radiating energy from within. That could explain the unexpected temperature plateau. Unfortunately, there's no way to confirm such a structure remotely. Radar reflection could, but that's impossible during conjunction. Once it reappears, NASA's Goldstone antenna may attempt low-frequency radar pings if the object's distance and orientation allow it. Until then, every scenario remains hypothetical. The models run endlessly. Some show the object glowing red-hot, shedding fragments into a tail. Others depict it remaining intact, sheathed in plasma, gliding through like a knife through light. The truth is somewhere in between. But one fact remains immutable. Whatever happens now, it's happening beyond our reach. In the command rooms of observatories across the world, monitors display only the Sun, a searing orb hiding a mystery behind it. Scientists take turns watching graphs that haven't changed in hours. There's nothing to analyse, no data stream, just the hum of computers running predictions. The heat encounter is unfolding unseen, and everyone knows that when 3I Atlas reappears, it may not be the same object that vanished. And this is where the story tightens, because heat doesn't just test matter, it exposes intent. The way an object behaves under stress reveals its design, whether by nature or by will. When 3I Atlas emerges from the Sun's glare, we'll see which force shaped it. For now, we can only imagine the scene, a dark interstellar body, wrapped in searing plasma, enduring the radiation storm of our star. Maybe it's fragmenting, maybe it's turning, maybe it's doing something no one expected. But one way or another, this encounter with heat will leave its mark, and when it's over, the silence we're hearing today may break, with signals, data, or light curves that force us to rethink what we've been tracking all along. The question now is simple. If the heat doesn't destroy it, what does it reveal? For the first time in months, every channel that once echoed with data from 3I Atlas is now quiet. No telemetry, no updates, no press releases, just silence. And in this kind of story, silence is never neutral. It can mean stability, or it can mean something went very wrong. When an object vanishes behind the Sun, standard protocol dictates a communication pause. Instruments are powered down or redirected, radio signals are minimized to prevent interference, and observatories shift to standby mode. But this time, the silence feels orchestrated, measured, deliberate, and far too synchronized across agencies to be ordinary. Since October 27th, NASA, ESA and JAXA have collectively entered what insiders refer to as a quiet zone. Even the Solar and Heliospheric Observatory, usually quick to publish raw data, has delayed updates. The reason given is data integrity assurance. In plainer words, too much noise, not enough clarity. Yet beneath that bureaucratic phrasing lies a tension that everyone in the field can feel. Because when agencies go dark, they rarely all do it at once. The quiet is amplified by context. In the weeks before conjunction, 3I Atlas had become one of the most watched objects in the inner solar system. Spectrometers at Mauna Kea, infrared telescopes in Chile, and multiple orbiters, from the Solar Orbiter to the Parker Probe, had collected terabytes of data. Every minor anomaly, every brightness change, every trace of nickel or carbon emission was tracked hourly. Then, without warning, everything stopped. The final data transmission cut off just as the object crossed the sun's line of sight. That's standard astronomy, but this isn't a standard object. The last sequence of images from October 28th showed the object brightening unexpectedly. A steady rhythmic pulse in infrared, 1, 2, 3 peaks, then darkness. The last signal caught it at a magnitude slightly higher than expected, implying a thermal event or reflective flare. Since then, nothing. Inside research teams, the word controlled has started to circulate. Controlled light emission, controlled trajectory stability, controlled silence. It's the third phrase that matters most right now, because when data transmission stops, interpretation fills the gap, and interpretation breeds fear. There's a deep irony in how the most technologically connected era in history still succumbs to blackout. No matter how advanced our instruments, the sun remains a firewall that no signal can cross cleanly. Radio waves scatter, optical sensors overload, plasma interference floods the channels. Even interplanetary probes lose contact during conjunction, their messages reduced to static until geometry shifts again. This happens every time, but this time the silence carries weight. That's because 3I Atlas isn't just another cosmic rock, it's a foreign body, moving through our system on a trajectory that doesn't belong here. And over the past months, every time the scientific community thought it understood the pattern, the object defied it. Its light curves didn't match models. Its jets didn't follow thermodynamic expectations. Its velocity remained oddly stable, even after measurable energy outbursts. That kind of behavior turns ordinary silence into potential signal. The absence of information becomes information itself. If the object were fragmenting, brightness would spike briefly, then fade. If it were outgassing, we'd expect gradual luminosity loss. But total flatline, that's neither. The sensors didn't just lose signal, they lost fluctuation. Every frequency band from radio to visible light went uniformly blank. It's like watching the heartbeat of a system suddenly stop, not violently, but intentionally. Within observatories, teams are debating what to do with that kind of void. You can't analyze silence, but you can measure its duration. And that's exactly what they're doing. The quiet has now lasted 42 hours. That's longer than most post-conjunction interference windows. In every prior mission, Mercury transits, Parker passes, even Venus radar experiments, residual static persisted. This time, it's pure emptiness. That purity suggests shielding. The possibility that 3I Atlas, whatever it is, has an exterior capable of blocking or absorbing radiation at frequencies that normally scatter. Some hypothesize a plasma sheath, created naturally by interaction with the solar wind. Others imagine something less natural, an engineered magnetic cocoon designed to survive stellar proximity. In either case, the effect is the same: total radio silence. It's easy to dismiss this as science fiction. But the data supports at least part of it. Before conjunction, magnetometers on the Parker Solar Probe recorded small but consistent deviations in field density along the object's projected path. Nothing conclusive, but enough to suggest magnetic interference not explained by background solar activity. That's a signature of something either ferromagnetic or actively interacting with charged particles. If that interaction intensified behind the sun, it could create the radio vacuum we're seeing now. Meanwhile, the human side of this silence grows heavier. Astronomers are trained to live by data, to find certainty in noise. Without it, they're left to inference. Every minute that passes without a return signal deepens the unease. For some, it's professional frustration. For others, it's existential. One astrophysicist at ESA, speaking off record, said, "It's like losing sight of a moving submarine. You don't know if it's still there or if it's turned toward you." The metaphor isn't accidental. Objects from interstellar space carry with them the unknowable, the possibility of intention. Even if 3I Atlas is a completely natural relic, its path through our solar system brushes too close to patterns of control for comfort. It's moving in harmony with orbital mechanics, but with precision so sharp it feels guided. That's the root of the anxiety that hangs over the silence. There's also the issue of withheld data. While no public updates have been released, some observatories continue collecting solar field readings that could reveal indirect evidence of the object's passage, yet none of those have been published. That's unusual. In most conjunction events, raw data streams are made public, even if corrupted. This time, only older datasets remain accessible. Analysts have noticed metadata inconsistencies in several archives, timestamps redacted, access restricted. That doesn't prove concealment, but it fuels the suspicion that someone, somewhere, knows more than they're saying. And so the public narrative collapses into uncertainty. On one side, the official line, technical blackout, standard interference, wait for reappearance. On the other, a growing chorus of independent researchers suggesting something else might be happening. Perhaps the object has shifted trajectory, perhaps it's undergoing internal transformation, or perhaps it's emitting signals beyond our detectable range. Signals, that word keeps returning, because silence doesn't necessarily mean inactivity. It can mean change in frequency. The sun's radiation blinds our instruments across most known bands, but there are regions, deep in X-ray, deep in submillimeter, where data can still pass. If 3I Atlas emits within those windows, we wouldn't even know to look. For that reason, the Chandra X-ray Observatory has quietly scheduled follow-up observations for early November, immediately after conjunction ends. The goal isn't just to photograph the object, it's to detect any residual high-energy emission that could indicate controlled thermal output. That kind of scheduling, done quietly and on short notice, signals that not everyone is treating this blackout as routine. Still, the scientific process requires patience. Instruments can't be pointed blindly near the sun. One misalignment could damage them permanently. The strategy now is to wait until November the 3rd or 4th, when the angular separation widens enough for safe imaging. Only then will we know if the silence was purely geometric or something else entirely. Meanwhile, thermal simulations continue. If the object is absorbing heat without venting it, internal pressure could be rising. Think of it as a sealed vessel under extreme stress. At a certain threshold, either the structure yields or it releases energy. The question haunting mission planners tonight is whether that release, if it occurs, would be visible or contained. A contained burst might resemble nothing at all, just continued silence. The controlled nature of this event also extends to human behaviour. Teams have been instructed not to speculate publicly. Some scientists have even received temporary media restrictions under the guise of communications discipline. It's an odd phrase, one normally reserved for defence operations, not astronomy. Yet here it is, applied to an interstellar object. The result is a total informational lockdown. That absence of communication has created what some insiders call the gap, a span of time during which humanity knows an object of unknown origin is undergoing transformation near the sun, and no one can talk about it. For an age obsessed with transparency, that's an uncomfortable reality. The data isn't gone, but the context is sealed, and so the story evolves into something more psychological. It's no longer about telescopes and trajectories, it's about trust. Can the public trust institutions that fall silent at the same moment an interstellar object disappears behind the sun? Can scientists trust their own models when the last few readings already defied them? And can anyone truly trust that silence means nothing more than interference? For now, silence is the only constant. It stretches across space, across disciplines, across screens glowing in dark observatories. Scientists refresh data logs knowing nothing new will appear. The hum of air conditioning replaces the thrill of discovery. Everyone waits for a flicker, a frequency spike, a whisper of the object returning. But the longer the silence lasts, the more it begins to feel like a message in itself. A message defined not by what it says, but by its refusal to say anything at all. Soon, this silence will end. The object will emerge from behind the sun, and with it, data will flood in again. But whether that data confirms expectations or rewrites them entirely depends on one question. Was this just nature's quiet, or was it control? Because if it was control, if 3i Atlas is somehow regulating its own visibility, then this silence isn't absence, it's intention. And when intention meets trajectory, the next step isn't communication, it's movement. Long before today's blackout, there was a pattern that divided the astronomical community. The orientation of 3i Atlas's jets. Most comets release vapor and dust in random directions, shaped by surface irregularities and rotational spin. But 3i Atlas didn't. From the first high-resolution captures in August, one of its primary emission plumes consistently pointed toward the Sun. That alone broke the model, because jets like that should push an object away from sunlight, not toward it. To understand why this anomaly matters, imagine lighting a rocket engine that always fires directly into the source of gravity pulling it down. That thrust would resist, not assist, orbital motion. And yet, despite this contradictory behaviour, 3i Atlas's velocity remained steady, its trajectory smooth. The jet neither destabilised nor decelerated it. Instead, it produced what looked like a subtle self-correction, like a fine-tuned vector adjustment compensating for gravitational pull. That's the puzzle. No known comet behaves that way naturally. Outgassing jets, when they appear, emerge from heat pockets exposed unevenly on the surface. They vary in intensity and direction as rotation exposes new regions to sunlight. But in every dataset recorded since its detection, 3i Atlas maintained a persistent sun-pointing emission, even as its angle relative to the Sun shifted over millions of kilometres. That's not a thermal accident, that's geometry. Astronomers have named this the alignment problem. The pattern appeared first in spectroscopy. Faint, repeating brightening in nickel emission lines synchronized with perihelion approach. Then, optical imaging confirmed a continuous streak, faint but detectable, running radially toward the Sun. It wasn't simply a tail, it was a directed vent. Here's why that's strange. Natural venting follows heat gradients. As a comet spins, sunlight migrates across its surface, activating volatile pockets sequentially. The result is a chaotic, flickering set of jets. But for 3i Atlas, the emission remained locked, like a gyroscope maintaining orientation regardless of motion. The odds of that happening purely by chance are infinitesimal, less than 1 in a million, according to models run at a Coroner observatory. So what could cause this? There are 3 leading hypotheses. The first is purely mechanical, a rotation period perfectly synchronized with orbital motion, keeping the same face toward the Sun. That would make 3i Atlas a spin-locked body, similar to how the Moon always shows one face to Earth. But for a small, irregular interstellar object moving at over 100,000 kilometers per hour, that kind of stable synchronization is nearly impossible. It would require precise angular momentum established long before it entered the solar system. The second hypothesis is structural. Some researchers propose that the object's surface may contain deep fissures that channel sublimation along specific paths, creating natural thrusters. If these fissures are symmetrically arranged, the combined force could mimic intentional control, yet that explanation fails when tested against the stability of the emission. Natural fissures degrade quickly under solar stress. Within weeks, their output changes. 3i Atlases didn't. The third explanation, the one that makes even seasoned astrophysicists uncomfortable, is regulation. That the jets themselves are responding to feedback, adjusting based on external conditions. Not artificial intelligence, not consciousness, just an active mechanism, perhaps electrochemical, that maintains balance. If such a mechanism exists, it would be the first recorded example of adaptive behaviour in a non-biological, non-human object of interstellar origin. During September, when the object was still visible, the James Webb Space Telescope's mid-infrared spectrometer picked up subtle rhythm in the emission cycle, pulses every 11 minutes, matching slight fluctuations in brightness. At first, the data was dismissed as instrumental interference. Then, multiple observatories confirmed it. The pulses weren't artifacts. They were real. 11 minutes, over and over. The timing didn't match rotation. It didn't match precession. It matched nothing known. Those pulses stopped only when the object approached conjunction, disappearing into glare. Now the question is whether that alignment, sunward, pulsing, consistent, still continues behind the Sun. If the pattern persists, it means 3i Atlas is executing an incredibly precise thermodynamic operation, directing material loss not randomly, but in response to solar input. That would make it the first known object to use radiation pressure as part of its dynamics, rather than simply suffer from it. Some at NASA's Goddard Space Flight Center have quietly tested models, assuming the jet acts like a compensatory thruster. The results are unnerving. Even with minimal thrust, equivalent to the vaporization of a few kilograms per second, the object's trajectory could be stabilized within a narrow range of orbital parameters. The math works perfectly if and only if the emissions are intentional. Then there's the question of the material itself. Nickel and carbon compounds, under high heat, can create photoionized plasma streams that align magnetically. If 3i Atlas contains trace magnetic ordering, say residual magnetite or artificial ferromagnetic structures, those jets might orient themselves naturally toward the largest magnetic source nearby, the Sun. But the consistency of the alignment suggests a higher order effect, something more than magnetism alone. The solar orbiter recorded a peculiar signature before the blackout, a faint uptick in magnetic flux coinciding with 3i Atlas's position vector. The spike was brief, only a few seconds, but distinct from the solar background. It hinted that the object might not only align to the Sun, but interact with its magnetic field, anchoring itself within the heliospheric current sheet like a filament. If true, that would make 3i Atlas the first interstellar object to demonstrate magnetic coupling behavior. Here's what that means in plain terms. Instead of being pushed by solar radiation, it could be surfing it, riding magnetic gradients the way a sail rides wind currents. Controlled or not, that's a form of navigation through energy. As the blackout continues, this question lingers in every control room. What if the alignment is still active? If the jet remains sun-pointing even as the object passes through perihelion, it implies a feedback system functioning at the hottest, most chaotic part of its trajectory. That's like watching a spacecraft maintain perfect thrust control in the middle of a star's corona. Skeptics argue that we're overfitting patterns to noise, that human minds crave structure even in randomness. But that argument grows thinner with every anomaly that stacks without breaking consistency. When randomness persists in an ordered way, it stops being randomness. Still, scientists tread carefully. The word artificial remains forbidden in official discussions. Instead, they use terms like non-gravitational acceleration and thermochemical regulation. But beneath those sterile phrases lies the same implication. Something about 3i Atlas behaves as if designed. To illustrate, imagine its motion plotted in a simulation. A normal comet's jets produce jitter, tiny deviations in trajectory that accumulate into measurable drift. 3i Atlas's path shows the opposite, self-correction. When solar radiation should push it slightly off course, it steadies. When gravitational tides should tug, it compensates. Over time, the error margins cancel out. The more data you feed into the model, the more it looks like feedback control, not chaos. The European Space Agency's tracking division has privately compared its motion to known spacecraft stabilization profiles. They don't match perfectly, but the pattern's signature smoothness resembles controlled vector alignment. Not a single wild fluctuation since August. If this alignment continues unseen behind the Sun, it could mean that what we're calling a jet isn't a natural vent at all. It's a propulsion vector. The implications of that are staggering. It would mean that 3i Atlas, an object billions of years old, travelling through interstellar space, is performing controlled thrust operations near the heart of a star system. Even a single percentage point of probability in that direction transforms it from a curiosity into a message, not a transmitted one, but a physical demonstration of possibility. And yet, all of this remains inference. The telescopes are blind. The Sun is a curtain. No one can confirm whether the jet still burns or if it's quiet now. The only clue will come when 3i Atlas emerges, if its trajectory has shifted or if its spin rate has changed. If those data points show any deviation from the gravitational model, then the debate ends. It will no longer be about whether the jet was aligned. It will be about why. In every lab tonight there's an unspoken thought. Maybe this is the moment the object changes course. Maybe that's why the silence feels controlled. If the alignment is more than a thermal reaction, it could mean the object isn't just surviving the Sun, it's using it. Harnessing heat and gravity to adjust position, unseen, while every human eye is blinded. In that sense, the jet alignment isn't a mechanical detail, it's a maneuver, a hidden act happening in the brightest place imaginable, and when the sun's glare fades in the coming days, the first images we capture might show more than light. They might show evidence of intent. Until then, the models keep looping and the silence stretches on. Every second behind the sun feels like a choice, either a natural endurance test or the execution of a plan no one on Earth can yet comprehend. And if that plan involves motion, then we need to understand where it's going next. When 3i Atlas finally emerges from behind the sun, every observatory on Earth will be waiting for one thing: a number, not a picture, not a signal, just a shift, even a fraction of an arcsecond in its predicted position. That single deviation, no matter how small, could mean everything, because trajectory doesn't lie. It's the language of celestial mechanics, clean, mathematical, immune to interpretation. Every object that moves through space obeys the same laws: inertia, gravity, radiation pressure. But if 3i Atlas's path changes in a way that can't be explained by those forces, then something else is acting upon it. Either a hidden natural mechanism or an external one. Either way, the silence of the past few days will suddenly make sense. Let's start with what should be happening right now. Based on orbital integration, 3i Atlas is sweeping through perihelion, the closest point of its trajectory to the Sun. At this distance, solar gravity exerts nearly 20 times the force it experienced just weeks ago. The object's velocity peaks around 114 kilometers per second, faster than any spacecraft ever built. It's moving through a region of space where solar wind particles strike with relentless intensity, and the Sun's magnetosphere curls like invisible surf. In theory, that combination of forces defines its future path with near-perfect precision. We can model it, predict it, and plot it decades in advance, but that's only true if nothing interferes. For a normal interstellar object, trajectory after perihelion should follow a smooth hyperbolic arc outward, a clean escape from the Sun's influence. For 3i Atlas, however, there's one catch. It's already shown signs of non-gravitational acceleration. In late September, radar tracking from NASA's Deep Space Network measured a deviation of about 0.03 millimeters per second squared, minuscule but statistically significant. That same anomaly appeared again in early October, confirmed independently by the European Southern Observatory. The direction of that drift aligned not away from the Sun, as sublimation-driven acceleration would suggest, but sideways, along its orbital tangent. That made no physical sense, unless, of course, the object was producing controlled vector thrust. Now, with the Sun's heat at its maximum, every model diverges. The gravitational solution, the simplest one, predicts the object should emerge around 3 degrees east of the Sun on November 3rd. But if the sideward acceleration persists, even slightly, it could reappear a few thousand kilometers off course. That offset might sound trivial, but at interstellar speeds it represents a deliberate redirection. It's easy to underestimate how sensitive these measurements are. When Oumuamua was tracked in 2017, its deviation was only 0.0001 millimeters per second squared, barely enough to detect. Yet that tiny force reshaped its entire post-solar trajectory. If 3i Atlas's thrust is even 10 times greater, the consequences are enormous. It could alter its path by millions of kilometers before it exits our system. Scientists at the Jet Propulsion Laboratory are already preparing 3 predictive trajectories. The nominal path, purely gravitational, no drift. The object exits toward the constellation Pegasus by early 2026. The accelerated path, non-gravitational push consistent with nickel outgassing. Object exits at a slightly higher inclination, leaving the ecliptic plane. The controlled path, sustained thrust that stabilizes at constant orientation, implying active vector management. The difference between these models is measured in micronewtons, but the implications stretch across light years. Because if the third model fits the data, we're looking at something unprecedented. An object steering itself through a star system. This is why the coming days matter so much. The blackout isn't just an observational inconvenience, it's a blank line in an equation. Without data during conjunction, we can't confirm whether the trajectory evolved naturally or deliberately. By the time it reappears, the evidence will already be written into its motion. Imagine the tension in those control rooms. astronomers running simulations in real time, fine-tuning orbital elements by decimal places, waiting for the first post-conjunction coordinates. If the new data matches the predicted curve exactly, the story ends quietly. But if it doesn't, even slightly, the questions begin. Because trajectory drift, more than any other variable, is where nature and design diverge. Take the example of comet Encke. It exhibits small, consistent deviations from gravity due to outgassing, but they're irregular and temperature dependent. Now compare that to 3I Atlas. Its previous deviations followed a perfect sinusoidal curve, periodic, symmetric, and independent of solar distance. That's not random venting, it's calibration. Calibration suggests intent, or at least internal feedback. And if feedback exists, the object isn't simply reacting, it's adapting. Behind the Sun, as radiation pressure peaks, the physics of trajectory becomes even more delicate. Solar gravity pulls inward, radiation pushes outward, and electromagnetic drag tugs sideways. The balance of those three forces determines the arc of escape. A natural body might wobble slightly as gases vent unevenly. A regulated one, however, could use those same forces to maneuver with precision, exploiting them like currents. Some researchers suspect that 3I Atlas's sun-pointing jet, if still active, could function exactly that way, not as propulsion, but as stabilization. By continuously venting in opposition to solar wind, it could counteract torque and maintain course. That kind of vector control would be indistinguishable from guidance, but there's a darker possibility that the drift is not stabilization at all, but redirection. The object's path is projected to pass about 0.34 astronomical units from Earth's orbit by mid-December. That's roughly 50 million kilometers, a comfortable distance by cosmic standards. Yet if its trajectory were to shift by only 0.02 degrees, it could shorten that gap by half. A minute change today could translate into millions of kilometers difference later. That's why tracking is so critical, and why the blackout feels like a missing heartbeat. NASA's orbital analysts are confident the object poses no threat. The mathematics still places it well clear of Earth's gravitational sphere, but the timing, late December, coinciding with its outbound phase, has fueled speculation among independent researchers. Some claim the object's path is deliberately synchronized with Earth's orbit, that it's performing a flyby. Others dismiss that as pattern-seeking paranoia. The truth will come down to measurement, not belief. At the European Space Operations Centre in Darmstadt, teams are preparing automated observation scripts for reappearance. Telescopes will fire in synchronized intervals, triangulating position across multiple wavelengths. Within minutes of the first detection, orbital recalculations will update globally. It will be one of the most anticipated coordinate checks in recent astronomical history, not because of danger, but because of meaning. Trajectory reveals motive. Even in the language of physics, motion can imply decision. The analysts studying the object's drift have found another peculiar clue. When they plot its velocity vector against solar longitude, the residuals, the tiny mismatches between prediction and reality, form a repeating loop. Every few weeks the same oscillation recurs. No comet, asteroid, or interstellar rock has ever shown such cyclical drift symmetry. The only comparable curves are from controlled spacecraft performing gravity assist corrections. That comparison unsettles even those who reject the artificial argument. Because to reproduce such a pattern naturally, 3I Atlas would need perfectly periodic outgassing synchronized with its orbital speed, an implausible coincidence on an object tumbling through space for millions of years. And yet, the numbers are there. In physics, coincidence has limits. Beyond those limits, coincidence becomes correlation. For now, there's only anticipation. Scientists have published provisional maps marking where the object should reappear along the solar limb. Amateur astronomers across the southern hemisphere are preparing to scan that region every dawn, hoping to spot the first faint shimmer. When that shimmer arrives, it will bring an answer to months of speculation, not in words, but in geometry. If the trajectory is unchanged, 3I Atlas remains an extraordinary but natural visitor. If the trajectory drifts, then something happened behind the Sun, something that altered momentum without external cause. In a sense, this is the purest form of evidence humanity can observe, an unambiguous physical shift. No interpretation, no interference, just movement where none should exist. And in that movement lies the truth. If the path bends, we'll have to ask, what force bent it? Not gravity, not solar wind, not coincidence, something else. Whatever emerges next week will determine which universe we live in, one where matter drifts by chance, or one where something out there navigates. And while the world waits for coordinates, another question brews in the laboratories. What exactly is this object made of, that it can endure such extremes and still steer its fate? For months, the light coming from 3I Atlas has been our only clue to what it truly is. Every photon reflected or emitted from its surface carried coded information about its chemistry, its structure, even its temperature. But now, that light's gone. The sun has swallowed it, and with it, our ability to decode the object's spectrum. What remains is a gap, a blank interval in the record that could hide the most important transformation in the entire mission. Spectroscopy is the heartbeat of modern astronomy. It tells us not only what something looks like, but what it is. By splitting light into its constituent wavelengths, we can identify the fingerprints of atoms and molecules, the hydrogen lines, the carbon bands, the metallic signatures that make each celestial body unique. Before the conjunction blackout, 3I Atlas's spectrum didn't match anything on record. It wasn't icy like a comet, nor stony like an asteroid. Instead, it displayed faint emission lines from nickel, carbon monoxide, and something else, an unstable compound that should have broken apart long before it reached the inner system. That compound, nickel tetracarbonyl, has become the center of the debate. It's toxic, volatile, and virtually impossible to sustain in high heat. And yet, repeated readings confirmed its presence again and again. The simplest explanation is that we were wrong. That instrumental noise mimicked the pattern. But if the signal was real, it implies chemistry that can only occur under pressure and controlled thermal conditions. The last clear spectrum, recorded on October 28th, contained one more mystery. The carbon monoxide absorption line, which had been broad and chaotic in August, suddenly narrowed to a razor-thin peak. That means the gas environment around 3I Atlas became more uniform, less turbulent, almost stabilized. Natural outgassing doesn't do that. It grows more chaotic as a body heats up. Stability under rising temperature defies thermodynamics. And then, the light vanished. The moment the object entered conjunction, every instrument tuned to its wavelength bands went blind. The James Webb Space Telescope had to reorient its mirrors away from the sun to avoid damage. SOHO's coronagraphs, overwhelmed by solar glare, could no longer isolate the object's faint emissions. Ground-based infrared arrays from Hawaii to Chile showed only a wall of noise. The result? For the next several days, there will be no new spectra. No confirmation, no updates. A spectral silence. For scientists who've spent months parsing every tiny fluctuation, that silence is maddening. Because spectroscopy doesn't just reveal presence, it reveals change. The moment 3I Atlas began heating, every compound on its surface would begin to react, break apart or recombine. Without direct observation, we won't know which of those processes occurred. If its nickel compounds vaporized, the characteristic 7.5 micron emission band would fade. If they didn't, the band should intensify as the object endures the sun's radiation. But at this distance, the only instrument capable of detecting that band, the JWST's MIRI spectrometer, can't risk pointing anywhere near the solar limb, and so the record stops. Astronomers call this kind of break a spectral gap. It's rare and usually harmless, but in this case, it falls precisely across the object's most critical thermal phase. Imagine filming a rocket launch, and the camera cuts out just as the engines ignite. That's what we're experiencing now, a missing sequence that could decide whether 3I Atlas is a natural body or something else entirely. In the absence of data, teams are turning to models. They feed the last known parameters, temperature, brightness, jet velocity, into chemical simulations, trying to guess what's happening now. Some models predict complete dissociation of nickel tetracarbonyl within minutes of perihelion, leaving behind only trace carbon soot. Others predict something more exotic, catalytic recombination forming a thin reflective crust that could protect deeper layers. If that's true, the object might not lose brightness, it might gain it, becoming more mirror-like as it endures the sun. This theory fits an odd historical pattern. Both Oumuamua and Borisov, the two previous interstellar visitors, showed unexplained albedo changes near perihelion. Each became unexpectedly reflective, as if polished by heat. 3I Atlas might be doing the same, only more dramatically. The difference is, we can't see it happen. A few instruments may still offer indirect glimpses. The Parker Solar Probe, currently orbiting inside Mercury's path, measures the density and temperature of the solar wind. If 3I Atlas interacts strongly with that flow, Parker's sensors might record subtle disturbances, ripples in charged particle velocity, changes in ion composition. Those fluctuations wouldn't reveal what the object looks like, but they could hint at chemical reactions releasing material into the solar wind. As of now, no such anomaly has been confirmed publicly. But data from Parker travels slowly. It could take weeks to process. Meanwhile, smaller observatories are scouring side channels for any trace of 3I Atlas's signature. Even a faint reflection in ultraviolet could reveal whether the object fragmented. But ultraviolet observation near the Sun is perilous. Most instruments simply can't risk it. So for now, every telescope stares elsewhere, waiting for the Sun to rotate enough to reveal the dark space beyond it. In that waiting, a deeper question emerges. What does a gap mean in the story of discovery? Science depends on continuity, on watching a process unfold, but 3I Atlas keeps breaking that continuity. Every time it enters a critical phase, something blocks our view. In July, it was dust interference. In September, signal degradation. Now, the Sun itself. It's as if the universe, or the object, keeps choosing the moments when we're blind. Some researchers have begun using a different phrase, observational choreography. The idea that coincidence alone cannot explain the perfect timing of these interruptions. Maybe it's just geometry, or maybe the object's orbit is such that by pure chance, its key moments always occur when human instruments can't see. Either explanation challenges us, because if the object's trajectory was ever adjusted, even once, that choreography stops being coincidence. But that's speculation, and the data scientists cling to what's measurable. When the object emerges, the first thing they'll do is aim spectrometers back at it. If the nickel lines are gone, it means the compound broke apart. 3I Atlas is more comet than enigma. If the lines persist, or if new ones appear, then the material composition has changed in a way we can't yet explain. There's another possibility, though rarely discussed, that the object's emission spectrum could return cleaner than before, with sharper peaks and lower noise. That would imply a surface that has reorganized, perhaps melted, refrozen, or even crystallized. Metals under high heat can do that, forming self-healing lattices. If 3I Atlas's surface behaves that way, it may have just crossed from chaos into order. The silence of the spectral gap then becomes more than a pause. It's the interval in which transformation hides. Every great discovery in astronomy has one. A moment when the instruments can't see, and faith in the data gives way to imagination. Galileo had it when clouds covered Jupiter's moons. Hubble had it when his telescope blurred its first light. And now humanity faces its own modern blindness, a gap in the light of an interstellar object at the very edge of comprehension. In a few days, the Sun will turn and the gap will close. When it does, the first spectrum that comes through will either confirm what we already believe or end the debate forever. Because spectra are truth. They can't be faked, and they don't lie. Until then, all we can do is wait in the dark, knowing that somewhere behind the Sun, light continues to move, and that it's carrying answers we just can't reach yet. And when that light returns, it might reveal not only what 3I Atlas is made of, but something even stranger, how it manages to generate energy instead of losing it. Before the blackout, before the silence, there was a pattern in the data that no one could fully explain, a rhythm hidden in the heat. Every time 3I Atlas rotated, its infrared emissions pulsed. Not chaotically, like natural sublimation, but in intervals, controlled, repeating, 11 minutes, 22 seconds apart. It was first detected by the Subaru telescope in early September, confirmed later by JWST's MIRI instrument. The pulses weren't reflections, they were heat. Something on or inside the object was generating bursts of thermal radiation, small, precise, and consistent. At first, scientists thought it might be rotational. A spinning body sometimes flashes brighter when a reflective surface turns toward the observer. but the timing didn't match the object's estimated spin period. The pulses were too steady, too narrow in bandwidth, too localized in frequency. Infrared peaks like that suggest an energy source cycling through states, absorbing, releasing, resetting, and that's where things became impossible, because energy doesn't behave that way in deep space. A comet's heat rises gradually, following the curve of its approach. It doesn't oscillate. The sun doesn't heat in pulses, and 3I Atlas shouldn't cool in rhythm. Yet the emission curve looked mechanical, a sawtooth waveform repeating every 11 minutes, fading slightly over time then stabilizing again. When the object passed 0.7 astronomical units from the sun, the pattern changed. The pulses doubled, every 5.5 minutes a flare. Then, without warning, the amplitude flattened. The light grew uniform, as if the system had reached equilibrium. No one could explain it. To the engineers at NASA's Jet Propulsion Laboratory, it looked eerily familiar. The pattern resembled a heat regulator, the kind used to maintain temperature stability in spacecraft. When an onboard system cools below threshold, heaters activate. When it warms, they shut off. The cycle repeats with exact periodicity. That's what the 3I Atlas readings looked like. Thermal management, not thermal chaos. The implications were staggering. Was it possible that the object wasn't just surviving the sun's radiation, but actively managing it? Some researchers proposed a radical model, 3I Atlas as a conductor, a solid structure capable of storing and redistributing energy. Its metallic spectrum supported that theory. Nickel and iron, when structured in thin layers, can act like thermal capacitors. They absorb heat rapidly, then release it in bursts. In artificial systems, that process is called phase cycle regulation. But no natural body has ever demonstrated it on this scale. Even stranger were the spectral anomalies recorded during those pulses. Each thermal surge came with a slight spike in electromagnetic intensity around 0.9 microns, a wavelength associated with ionized carbon emissions. That shouldn't happen simultaneously with heat release. It's as though the object were converting absorbed radiation into charged particle emission, effectively using solar energy rather than simply absorbing it. To understand how extraordinary that is, imagine a rock acting like a solar panel, not reflecting sunlight, but processing it, taking the energy in, storing it, and releasing it in timed bursts. If that's truly what's happening, 3I Atlas isn't just resilient, it's efficient. It's performing an energy exchange with the sun. At the European Southern Observatory, one simulation explored this possibility in detail. It assumed the object has an internal lattice, metallic, conductive, semi-hollow, and that its nickel content behaves like a high-efficiency radiator. As it faces the sun, the surface absorbs radiation, raising its temperature. When it reaches critical heat, stored energy releases along fault lines, generating the observed jets and flares. The process then resets, repeating in cycles. The outcome? Controlled heat management through electromagnetic regulation. If this model is correct, it explains the strange stability of the object's brightness. Most comets brighten exponentially near the sun, then fade quickly. 3I Atlas's luminosity, by contrast, followed a flat curve, rising gently, plateauing, and holding steady for weeks. That's not random. That's feedback control. There's another theory, one that's whispered, not published. It comes from a handful of plasma physicists who've analysed the faint magnetic fluctuations recorded near the object's trajectory. They believe 3I Atlas might be surrounded by a thin, electrically charged sheath, a plasma boundary, that separates it from the surrounding solar wind. Within that sheath, heat could be redistributed magnetically. In human engineering terms, that would be a shield, a magnetoplasma bubble like those once proposed for interstellar propulsion. If that's true, then the energy pulses we detected weren't radiation leaks. They were corrections, stabilization bursts maintaining equilibrium inside the sheath, like a living cell regulating temperature. Of course, no official statement acknowledges that. NASA's last public note referred only to non-gravitational energy fluctuations consistent with outgassing activity. But even that phrasing, energy fluctuations, is unusual. Agencies don't use that term for comets. They use mass loss rate, or sublimation. The wording hints that something about the readings didn't fit either category. The blackout now hides the most crucial phase of all, the point at which the energy pattern should reach its peak. If 3I Atlas is truly performing heat regulation, the conjunction period would be the ultimate test. The sun's radiation pressure is now at maximum. A natural object would overheat and fragment. A regulated one would stabilize. When the silence lifts, we'll know which outcome prevailed. Behind closed doors, energy analysts are already preparing comparison charts. They'll overlay pre- and post-conjunction infrared data to see if the periodic pulses return. If they do, at the same timing, the same amplitude, it will mean the system remained intact through solar maximum. And if the timing changes, that could mean it adapted. That word, adapted, keeps surfacing quietly in internal memos. It's the only one that fits the pattern without invoking impossible explanations. Adaptation through physics, not through will. A structure responding intelligently to its environment without needing intent. But the border between adaptation and control is thin. If 3I Atlas emerges brighter, cleaner and stable, the implication will ripple far beyond astronomy. It will mean that interstellar space can preserve not only fragments of planets or dust, but functioning systems, remnants of engineering so ancient they drift across galaxies still alive with feedback. For now, there's no proof, only numbers, frozen mid-sequence, energy readings that end just as the sun's light swallows the object. The cycle stopped at its 11th pulse before blackout. If it resumes at 12, the story changes. When light returns, so will the truth. And the first infrared spike after conjunction will answer the question that's haunted this entire investigation. Was the heat we saw just physics, or was it power? Because if the pattern resumes exactly where it left off, the story of 3I Atlas stops being about what it is. It becomes about what it's doing. Every object that enters the inner solar system faces a trial by fire. The closer it moves toward the sun, the more violently the universe tries to unmake it. Icy bodies vaporize, rocky bodies fracture, metals soften, then disintegrate. The sun tests everything that comes near it, and 3I Atlas, right now, is undergoing that test at an intensity no natural traveller has ever survived intact. What keeps it together is, in many ways, the final unanswered question. Because if its internal composition is what early spectroscopy suggested, the laws of material physics are being pushed to their limits. Let's start with the basics. Temperature. At its current distance from the sun, roughly 0.3 astronomical units, the ambient radiation would heat any unprotected surface to over 1,200 degrees Celsius. That's enough to melt lead, to soften iron, to obliterate ice and carbon-based compounds. Any normal comet would already be gone, but 3I Atlas, just before vanishing into conjunction, wasn't dimming, it was brightening. That single fact demands explanation. Most scientists agree that for an object to survive at those temperatures, it must either reflect sunlight efficiently or possess an exceptionally high melting threshold. Reflectivity, measured as albedo, reduces heat absorption. A bright metallic surface can deflect up to 90% of incoming radiation, but 3I Atlas isn't bright. Its measured albedo hovers around 0.17, similar to dull nickel ore. That means it's absorbing most of the light that hits it, yet instead of burning apart, it remains stable. The only logical explanation is that the heat doesn't stay on the surface. It's being transferred inward, conducted and redistributed. And that tells us something extraordinary about the object's structure. It's likely dense, possibly layered, with materials designed or evolved to manage thermal stress rather than resist it. One of the first clues came from its density estimate. Using gravitational perturbation analysis, researchers calculated a mass-to-volume ratio far higher than expected for a comet-sized body. If accurate, 3I Atlas is at least twice as dense as solid iron. That would make it one of the densest macroscopic objects ever observed moving freely through space. Natural formation can't easily explain that. Most dense asteroids are remnants of planetary cores, stripped and cooled over billions of years. For an interstellar fragment to maintain such density, it would need to have formed under extreme pressure, perhaps inside a supernova ejector zone or a collapsed planetary mantle. But the chemical readings complicate the story further. Before the blackout, spectral analysis revealed traces of nickel, carbon and silicon, but almost no oxygen. That absence is baffling. Oxygen binds readily with metals, forming oxides that dominate most natural planetary materials. Without oxygen, nickel remains pure and highly conductive. Conductivity means heat and electricity can travel through it rapidly, equalizing energy across the structure. A body built primarily from pure nickel or nickel-carbon composites could absorb solar energy and spread it evenly, preventing localized melting. It would in effect self-stabilize under thermal assault. To understand how extraordinary that is, consider what happens to spacecraft heat shields. When they enter an atmosphere, ablation dissipates energy. Outer layers burn away, carrying heat with them. But once the shield thins too much, the vehicle fails. If 3I Atlas uses a similar principle, gradual erosion instead of catastrophic melting, it might explain the consistent material loss rates recorded weeks before conjunction. Not chaotic shedding, but measured discharge. Those measured losses were strange enough. Observations from late October indicated the object was losing about 12 kilograms of mass per second, less than 1/10 of what standard sublimation models predicted. That's extraordinarily low given its exposure. In other words, 3I Atlas was resisting ablation far more effectively than theory allows. The question is how? A few theories stand out. The first is phase shielding, alternating internal layers of metal and carbon acting like thermal shock absorbers. When heat penetrates, it doesn't travel straight inward but diffuses laterally through conductive layers, slowing the rise of core temperature. Similar structures are used in advanced heat sinks on Earth, but on a planetary scale, they're unheard of. The second theory is self-repair. Certain alloys, when heated beyond their recrystallization threshold, can realign their grain structures automatically. NASA has experimented with shape memory alloys for decades. If 3I Atlas's surface behaves similarly, melting microscopically, then refreezing into a stronger configuration, it could explain the absence of fragmentation. Instead of cracking, it anneals. Instead of breaking, it hardens. The third theory, whispered among materials scientists, is more unsettling: metastable design. In this model, the object isn't static at all. Its interior rearranges under stress, redistributing mass through internal cavities or channels. Some models simulate this using ferrofluids, magnetically responsive liquids that reconfigure in real time when exposed to magnetic fields. If the object contains ferromagnetic materials, solar magnetism itself could be triggering self-organizing patterns inside it. The Sun, in other words, wouldn't be destroying 3I Atlas, it would be activating it. Evidence for that idea is thin, but not non-existent. In the last magnetometer readings before the blackout, the solar orbiter detected faint periodic distortions in local magnetic field strength, as if something conductive was modulating the plasma environment. The pattern repeated every few minutes, matching the infrared pulse cycles described earlier. It's the kind of resonance produced when an object interacts with a magnetic field dynamically, not passively. To the scientist analysing these data, it looks less like coincidence and more like coupling, a feedback loop between material structure and solar environment. The object isn't being acted upon by the Sun alone, it's responding. Now, during conjunction, that feedback has reached its apex. The Sun's radiation pressure and magnetic field are strongest here. If 3I Atlas is indeed reactive, it could be undergoing massive internal realignment right now, invisible to every telescope on Earth. What would emerge afterward might not be the same object we saw before. Its density, reflectivity, even shape could have changed. The object's surface geometry provides more hints. Images taken by the Very Large Telescope just before it vanished show irregular, ridge-like features stretching along its length, symmetrical enough to look patterned. These aren't random fractures. They're aligned with its rotation axis, as if stress distribution follows a designed architecture. Some speculate these ridges could function as radiators, channels for excess heat to escape, while maintaining overall integrity. A body with that kind of structural logic would endure conditions that should be fatal. It might even rely on them. In such a system, solar radiation isn't a threat, it's fuel. If that sounds speculative, consider this. A metallic lattice with sufficient purity can reflect part of the solar spectrum while absorbing specific bands, particularly in the ultraviolet. Those absorbed frequencies generate currents in the material itself. On Earth, we call that photovoltaic conduction. In space, on a massive scale, it could act as an energy stabilizer. The hotter it gets, the more power it redistributes, forming a closed thermodynamic loop. That's not fantasy, that's physics. Just not physics we've ever seen in an uncrewed object crossing interstellar space. And if that's what's keeping 3I Atlas alive, then the next few days will show whether its structure can truly endure perpetual stress. When it re-emerges, every telescope will measure its albedo, density, and surface composition again. If the readings match pre-conjunction values, the object survived unchanged. But if they show even minor shifts, new spectral lines, altered reflectivity, it would mean metamorphosis, material that adapts, structure that responds, matter behaving as mechanism. Behind closed doors, material scientists are already preparing contingency papers. Some speak of interstellar engineering relics, fragments of machines long dead, still performing automatic stabilization millions of years later. Others insist that the laws of mineral physics can still account for everything, given the right combination of elements and pressures. But even the skeptics admit this much. 3I Atlas has withstood forces that would have pulverized any comet, melted any asteroid, and vaporized any craft humanity has ever built. Whatever it's made of, it's stronger than anything we know. And that strength raises a new, uncomfortable question. What happens if it doesn't just survive the sun, but uses it? What if the stress we're watching isn't destruction at all, but ignition? Because as it passes through the most dangerous region of the solar system unbroken, one thought now hangs over every observatory. What if, behind the sun's glare, something inside 3I Atlas is activating? Right now, 3I Atlas is completely invisible. It's buried somewhere behind the sun's radiant wall, a point of blinding geometry where no telescope can reach. But invisibility doesn't mean stillness. In fact, this is the moment when everything we can't see matters most. Because when the object reappears, even a fraction of deviation in its spin, shape, or speed will reveal what really happened behind the sun. Every interstellar object moves, but not all motion is the same. Some drift through space passively, shaped only by gravity. Others, and there are very few in this category, exhibit signs of non-gravitational movement, slight accelerations, rotational changes, torque, none of them ever fully explained. And right now, 3I Atlas may be doing exactly that, evolving in silence, altering its orientation or velocity in ways that no one can yet detect. In the days before the blackout, photometric data from Chile showed subtle modulation in brightness, tiny variations that repeated every 43 minutes. That pattern hinted at rotation, but then, just 2 days before conjunction, the modulation stopped. The object's light curve flattened out completely. Either it stopped rotating or it rotated in perfect alignment with its orbital plane, hiding all variations from Earth's perspective. Both possibilities are troubling. If the rotation simply slowed, something had to sap its angular momentum. That requires force, outgassing, internal redistribution, or external magnetic braking. If it aligned precisely with the sun, it would mean control, a self-stabilizing moment when torque is corrected intentionally. Both outcomes violate expectation, and this is where the real mystery lies. When astronomers can't see an object, they turn to models. But every model of 3I Atlas diverges behind the sun. Some show it continuing to spin normally, others predict tumbling instability. A few, the ones no one wants to publish yet, show a third possibility, an orientation lock, where the object maintains a constant facing relative to the sun, despite torques that should disrupt it. If that's true, then something behind the sun is maintaining balance. We've seen versions of this before. Spacecraft aligning solar panels to the sun, small probes adjusting spin to regulate temperature. But this isn't a spacecraft. This is a body several hundred meters long, moving at more than 100 kilometers per second. The energy required to sustain orientation under those conditions is staggering. It would mean that the same mechanism controlling its jets and managing heat could also be controlling its spin. The last magnetometer readings from the Parker Solar Probe, taken hours before conjunction, showed something odd. Faint oscillations in the magnetic field strength, rhythmic, spaced at nearly the same 11-minute interval as the infrared pulses seen earlier. That rhythm shouldn't exist in solar wind data. The sun's magnetic fluctuations are chaotic, fluid, constantly shifting. A stable periodic signal in that environment is impossible, unless something is generating it. It's possible those oscillations were caused by 3I Atlas's passage through the solar wind, a wake effect. In plasma physics, moving conductive bodies can induce organized currents around them, carving paths through charged particles like boats cutting waves. If 3I Atlas has a metallic core or magnetic sheath, it could be doing exactly that, bending plasma flow in rhythm with its own internal cycles. In that case, its motion isn't just mechanical, it's electromagnetic. That's why this hidden period matters so much. While it's behind the Sun, it's in the most extreme magnetic environment in the solar system. The place where the Sun's open field lines reconnect, twist and whip outward in massive current sheets. If 3I Atlas interacts with that environment, it could be absorbing, storing or redirecting magnetic energy in ways that no natural object ever could. At the European Space Operations Centre, some analysts are calling this phase the field test. Not metaphorically, literally. A moment when the object's composition and structure are tested by the solar field itself. The Sun is forcing it to reveal how it handles stress, rotation, and charge simultaneously. What happens inside that crucible could decide whether it emerges intact or fragmented, or changed. If its orientation is stable when it reappears, the implications are staggering. Spin stability under magnetic torque would indicate active compensation, magnetic or gyroscopic. But if its rotation speed has changed dramatically, that would mean something even stranger: mass redistribution. In human engineering, redistribution is how spacecraft correct spin. They move internal components, gyros, propellant or liquid slosh tanks, to change moment of inertia. But in a solid interstellar object, the only way for that to happen is if the internal structure itself moves. Maybe molten metal flows beneath the crust, or magnetic channels shift material in response to field pressure. It's pure speculation, but so was every explanation for Oumuamua's acceleration until the data forced the discussion. There's also another scenario. The object could be hollow. If 3I Atlas contains voids, chambers, fractures, cavities, solar radiation could be generating internal pressure differentials producing torque from within. A single vent timed correctly could reorient the entire body. That's not impossible. But for it to align perfectly with solar geometry, to face the Sun continuously for days, would require a precision no random fracture could achieve, and that precision, repeated over time, begins to look deliberate. Meanwhile, the Deep Space Network continues to monitor background noise near the Sun's limb. Even during blackout, some frequencies slip through, scattered reflections of solar radio bursts. In those data, analysts sometimes find gaps, narrow windows where interference momentarily dips. A few of those dips correspond exactly to where 3I Atlas should be. Some suspect those are coincidences. Others think the object might be absorbing or reflecting specific radio frequencies. If that's true, then its hidden motions could involve more than mechanics. They could involve electromagnetic modulation, subtle shifts in how it interacts with radiation. If the object is modulating radiation, even passively, it's functioning as a resonator, a structure that vibrates in harmony with the solar environment. The physics of that resonance could explain much of what we've seen: the heat regulation, the magnetic coupling, even the recurring energy pulses. In that model, the object is not just surviving the Sun, it's communicating with it. But what would that communication look like? Not signals in the human sense, but oscillations, feedback loops between matter and field. If the object's internal composition is reactive enough, it might automatically align with magnetic flux lines, creating an energy exchange that stabilizes both itself and the surrounding plasma. That would explain the strange steadiness in its earlier trajectory and the mysterious silences in the data whenever the Sun's activity peaked. Perhaps the Sun isn't just blinding our instruments. Perhaps 3I Atlas is using the solar field to hide, folding its signal into the background, indistinguishable from the noise. All of these possibilities hinge on one upcoming event: its reappearance. When it emerges from the Sun's far side, telescopes will immediately measure its rotational light curve. If the rotation period is the same, the object was inert. If it's different, faster, slower, or phase-shifted, something happened. A force acted upon it, unseen. And if the axis itself has shifted, if 3I Atlas now spins in a new direction, that will confirm everything scientists have feared or hoped, that behind the Sun the object moved itself. Hidden motions, by their nature, can't be witnessed. They can only be inferred. But inference is often where revelation begins. The silence of the past days may not be absence. It may be motion so subtle, so perfectly masked, that only the aftermath can prove it. And that aftermath is now imminent. In less than a week, the first telescopes will open their domes at dawn, scanning the Sun's eastern edge. Somewhere beyond the light, a small dark body will emerge, spinning, glowing, or perhaps perfectly still. Its orientation will tell us everything. Because when something vanishes behind a star and returns with even the slightest change, it means that the time we couldn't see was the moment everything happened. The blackout isn't just a pause in observation, it's a chapter of transformation written in heat and magnetism. And when that chapter ends, the universe will reveal whether 3I Atlas merely survived the sun or used it. The next step is unavoidable, the reappearance. At dawn, the waiting will end. Every major observatory on Earth has synchronized their instruments for a single moment. The first reappearance of 3I Atlas from behind the sun. It will emerge slowly, rising from the solar glare like a dark speck against the burning light. And in that first frame of visibility, the story of the past week will be revealed. The world has been blind for 7 days. No data, no updates, just equations, predictions, and silence. But in those equations lies expectation, a map of where the object should be, how fast it should move, and how bright it should shine. If any of those variables deviate even slightly, it means something happened behind the sun, something we missed. At the European Southern Observatory, technicians are already rehearsing the capture sequence. At 0522 UTC, the chronographs will open. The cameras will engage in 5-second bursts, imaging through multiple filters: visible light, near-infrared, and ultraviolet. The goal isn't beauty, it's precision. They'll be looking for motion, for light curves, for symmetry. The very first pixel that shows deviation from predicted brightness will send alarms across the network. NASA, ESA, and JAXA will each be running their own observations in parallel, triangulating the object's position to within a few kilometers. The Deep Space Network will listen in a radio silence just in case. The James Webb Space Telescope, safely reoriented, will aim not directly at the object but slightly off-axis to avoid glare. The hope is to catch reflected light bouncing from solar plasma around it. That reflection will contain the first post-conjunction spectrum, the one that decides what we know and what we only imagine. If 3I Atlas survived intact, its light curve will rise slowly, stabilizing over the next 24 hours. If it fragmented, the brightness will fluctuate, showing the chaotic pattern of multiple bodies tumbling through sunlight. But there's a third scenario, one that scientists hesitate to name aloud: the possibility that it emerges stronger, brighter, more stable, and more coherent than before. That would mean something changed. Not destruction, not decay, but transformation. Shortly before sunrise in the southern hemisphere, amateur astronomers in Chile will have the first chance to see it. The skies there are the clearest on Earth, and their telescopes are already pre-calibrated to the expected coordinates, just 3 degrees east of the sun's limb. If they detect it early, even as a faint glint, it will confirm survival. But survival alone isn't the goal. Everyone is watching for the unexpected. The alignment, the rotation, the trajectory, all of it encoded in light and shadow. The most sensitive measurements will come not from Earth, but from orbit. The solar orbiter's onboard imagers will scan for magnetic anomalies near the sun's edge. Any distortion in solar wind flow could indicate interaction, the same electromagnetic behavior hinted at before conjunction. If 3I Atlas is still magnetically active, the readings will spike, and when those spikes align with reappearance, it will mean one thing: the object is alive, energetically speaking, still responding, still adapting. In every control room, the mood will shift from speculation to calculation. Software that's been running blind for days will suddenly have data to feed on. Predicted vectors will collide with reality. The numbers will either match perfectly, or they won't. If the trajectory matches the model, the story remains one of mystery but not miracle. An interstellar relic survived a stellar encounter, extraordinary but explainable. If it drifts, even slightly, the implications are profound. A change in velocity of just 0.01 meters per second would mean energy input unaccounted for by natural forces. A shift in rotation could mean internal reconfiguration. Either way, the object will have acted during blackout, and that means something happened when no one was looking. When the first images arrive, they'll spread fast. The world has been waiting, not just scientists, but the millions who followed every update, every rumour, every strange coincidence. The blackout has created tension unlike anything in modern astronomy. In the age of instant visibility, We're about to witness an event that no one could stream, no one could record, no one could monitor. It will come down to a single image, a small shape emerging from the sun's light, its edges haloed in glare, its surface glowing faintly blue, the same glow that defined it before it vanished. If that glow returns, the debate begins anew. If it doesn't, the mystery changes form. Because a silent object that moves naturally is one story. A silent object that reappears brighter after a week inside a star's corona is another entirely. When visibility stabilizes, the first full spectral scan will run through every available wavelength. Scientists will compare the new data against the old, line by line. If the nickel signatures remain intact, the object is chemically stable. If they've intensified, it means new surface exposure, possibly internal layers revealed. If new elements appear, silicon, chromium, or even trace rare gases, that would mean active chemical change, not passive erosion. And if the heat signature pulses again at the same interval, the 11-minute rhythm that defined it before, that will confirm everything the blackout implied: regulation, feedback, systemic stability. But if the rhythm changes, if the pulse is slow or synchronized with the object's new position, that will mean adaptation, that it learned from the sun, rebalanced itself, and re-emerged tuned to new conditions. For the scientists who've lived with this object for months, the reappearance isn't just data, it's confrontation. The moment when theory meets reality and speculation either collapses or becomes history. They've stared at graphs, numbers, and silence for days. Now, in that first glint of returning light, they'll face the one thing that data can't describe: motion with meaning. Whether natural or not, 3i Atlas has behaved like something with a plan, steady, deliberate, timed to the edge of perception. The universe doesn't owe explanations, but it does leave evidence. When it comes back into view, when the instruments capture its first full light, one truth will emerge. Maybe quiet, maybe shocking. It might show the same old object, inert, tumbling, ancient, indifferent. Or it might show something entirely different, reshaped, luminous, perfectly aligned with the sun, as if it learned how to live there. Either outcome will change how we see the cosmos, because survival itself, through that heat, that silence, that radiation, is already improbable enough to feel deliberate. In the next few days, humanity will look again into the light and see what came through it. And when 3i Atlas reappears, the question will no longer be what is it? It will be what has it become? The waiting ends not with noise but with light. When 3i Atlas finally emerges from behind the sun, there will be no explosions, no sudden flash, only a faint shimmer on a monitor somewhere, a quiet confirmation that it survived. Yet in that single shimmer lies 1,000 questions humanity isn't ready to answer. For 7 days we stared at nothing, a silence so absolute that even the instruments seemed to hold their breath, but that silence changed us. It forced the realization that not everything can be measured in real time, that discovery sometimes hides inside absence. Because when 3i Atlas disappeared, it wasn't the universe that went quiet, it was us. Soon the data will return, the first images will flood in, the first numbers will update, and the story will continue. But whatever emerges from behind the sun won't just be a rock or a relic, it will be a mirror, showing us the limits of what we can know and how small the gap is between science and wonder. Perhaps it will reappear unchanged, a survivor of heat and gravity, carrying the same riddles it brought from another star. Or perhaps it will return transformed, its surface reshaped, its energy recalibrated, its motion altered in ways no model can explain. In either case, something profound has already happened, because we looked into the heart of a star and waited for meaning to return. Every age of science has its silence, the moments when instruments fail, when light vanishes, when knowledge stops at the edge of perception. This was ours, and what we find now will remind us that not all mysteries exist to be solved. Some exist to remind us we are still capable of awe. So tonight, as telescopes realign and data streams flow again, one truth remains. Somewhere beyond that brilliant horizon, an object older than our solar system just faced the sun and lived. And whether it comes back brighter, darker, or changed forever, the question will linger like the afterglow of light itself. Was it endurance or intent?